Let's solve the following initial value problem. So here we have the given differential equation. First, let's consider this particular function and denote it with f of x comma y. Now when we make the substitution x with lambda times x and y with lambda times y into our function, we see that this will give back the original function f. And when this criterion is met, we say that our function f is a homogeneous function. And since our function is homogeneous, so this differential equation is a homogeneous differential equation. The next step will be to solve this differential equation, but the only issue here is we cannot use the method of variable separation. That's because we cannot express our function f as a product of two functions, g of x and h of y, where one of the function, which is g, is only a function of x and the other function is only a function of y. But if we make this substitution, y over x equals to v, then our differential equation reduces to a variable separable form. So let's do that. So y over x equals to v can be also expressed as y equals to v times x. And now we'll differentiate both sides with respect to x, and this is going to give us dy over dx equals to, apply the product rule to differentiate v times x, so that will give us v plus x times dv over dx. Now we can rewrite our differential equation as, so instead of dy over dx, we have v plus x times dv over dx equals to, so here we have y, so y will be replaced with v times x multiplied to x plus 2y, so 2y will be 2 times vx, divided by x multiplied to 2x plus y, so y here is v times x. So we can take x squared as the common factor in the numerator, so x squared multiplied to v multiplied to 1 plus 2v, divided by x squared multiplied to 2 plus v, and on the left hand side we have v plus x times dv over dx. So here x squared and x squared will get cancelled out, and next step we will subtract v from both sides. So we have x times dv over dx, and let's combine these two terms. So we have 2 plus v in the denominator, and in the numerator we have v times 1 plus v times 2v, that will be 2v squared, minus, so we'll multiply v with 2 plus v, so that will be 2v minus v squared. That means we have x times dv over dx equals to, so 2v minus v squared will give us v squared, minus v minus 2v will be negative v, divided by 2 plus v. Now we can separate the differentials to get 2 plus v divided by, so v squared minus v can be also expressed as v times v minus 1, means the same thing, multiplied to dv, and this is equals to dx over x. So that means we have successfully separated the differentials. Now we can integrate both sides. The integral on the right hand side, that's fairly simple. However, to integrate the integral on the left hand side, we'll have to use the method of partial fractions. So let's do the partial fraction first. So we have 2 plus v divided by v times v minus 1. So we will express it as a sum of two partial fractions, a over v minus 1 plus b over v. Let's multiply throughout with v times v minus 1. So we have 2 plus v equals to, so we'll get v times a plus v minus 1 times b. Now we have to find out the value of a and b. Let's start with a. To find out a, let's suppose v equals to 1. When we do v equals to 1, the second term vanishes. That will only leave us with a. So our a value will be equals to 3. And to find out the value of b, we'll have to get rid of the first term, which is v times a. So we'll let v equals to 0, and this is going to give us, so we have 0 minus 1, so that's negative b. So negative b will be equals to 2. That means we have b equals to negative 2. Or our partial fraction will be, so we have 2 plus v divided by v times v minus 1. So that will be equals to 3 divided by v minus 1 minus 2 divided by v. So our integral can be now expressed as we have 3 times dv divided by v minus 1 minus 2 times integral dv over v equals to integration dx over x. So let's find out the integral. These are very simple integrals. So we have 3 times natural log of v minus 1 minus 2 times natural log of v equals to natural log of x plus the constant of integration c. Right. Let's take natural log of c so that we can get rid of the logarithm by combining all of them. So we were going to use the property here. If we have log of a raised to the power of b, then this is simply equals to b times log of a. Since we have 3 times natural log of v minus 1, so we will have log of v minus 1 whole cubed. For this one, we have negative log of v squared equals to, we'll combine these two logarithms to get log of x times c. Then we can also combine these two logarithms to get natural log of v minus 1 cubed divided by v squared, and this is equals to natural log of x times c. Now we can get rid of the logarithm from both sides to get v minus 1 whole cube divided by v squared equals to x times c, or simply v minus 1 whole cube equals to x times v squared times c. What is v? So v will replace it with y over x minus 1 whole cubed equals to x times y squared over x squared times c. Or we get y minus 1 whole cubed, y minus x whole cubed divided by x cubed, and that's equals to, so here 1x and 1x will get cancelled, so we have y squared over x times c, or y minus x whole cubed equals to, we can cancel out 1x from here and 1x from here, so we'll have x squared. Let's cross multiply it, so we have x squared y squared times c. So this is a general solution. Now what we'll have to do, we will use the initial conditions, which is as given as y of 1 is equals to 2. That means when x approaches the value 1, y is going to approach the value 2. Fine. So let's use this. So we have 2 minus 1 whole cubed, that's equals to x squared, so that will be 1 squared times y squared, so y squared is 2 squared times c. So 2 minus 1, 1 cubed, that's 1 equals to 1 squared, 2 squared, so that's 4. So our c value is equals to 1 over 4. Let's substitute this value here. So we have y minus x whole cubed equals to x squared y squared divided by 4, and this is the final solution to our given initial value problem.